Welcome to Chapter 16, The Exploration to Inference, Part 2, Review. How we design for producing data is very essential if the data are intended to represent some wider population or process. This is the way to get a sample, a simple random sample. Remember, you take samples of a certain size, and any member of the population is equally as likely as any other member to be picked to be part of that sample. That's a simple random sample. Now, another way to get a good sample is called randomized comparative experiment. And we've talked about this. What we do is we randomly allocate different subjects to different treatments. Then we can compare the response. This gives us chance. And the use of chance in producing data is the central idea in statistics. It reduces bias and it allows us to use probability, the mathematics of chance, as the basis for our inference. Now, statistical inference draws conclusions about a population based on our sample. We've talked about this. And it uses probability to indicate how reliable the conclusions that we make are. So we learned about confidence intervals, and we learned about tests of significance. Now, a quick review of our confidence interval and what it really means is, remember, we take samples of a specific size, and we can take many, many different samples of this size, and we look at the means of each of those samples. And we construct a confidence interval about those different means. What will happen is that depending on how we constructed it, let's say we wanted to do a 90% confidence interval, then about 90% of those intervals will contain the true population mean. So when we talk about a confidence level, it really is the success rate of our method for the confidence interval. So we would say that, again, that if I did 100 confidence intervals of samples, let's say samples of size 15, I did 100 confidence intervals, approximately 90% of those would contain the true mean if I was doing a 90% confidence interval. Now, when we do tests of significance, we calculate a p-value, and that tells us how unusual the particular mean we took, the particular outcome, would be if the null hypothesis was true. So if the p-value is very, very small, that would say that it was something quite unlikely to have occurred, and that will tell us something about the null hypothesis. So if our p-value is very small, that's a good indication that our null hypothesis is probably incorrect, and we're going to reject our null hypothesis. But if the p-value is larger, then we're going to, and it would seem that the sample we took, the sample mean, was a value that was somewhat likely to occur, then we'll have insufficient evidence to reject the null hypothesis. Now remember, from Chapter 15 we talked about alpha. It's the probability of a type 1 error. And remember, the type 1 error is rejecting the null hypothesis when in fact it was true. So the probability of a type 1 error is alpha. In other words, we will set up the probability of making this particular error before we start our test. So in our class, we're going to set up the probability of making this particular error before we start our test. The p-value is the probability of a type 1 error based on our sample in the null hypothesis distribution. That's why we will only reject the null hypothesis if the probability of making this error based on our sample is less than alpha. In other words, our sample is telling us that the probability of making a type 1 error is less than alpha. And remember, we set up that alpha at the beginning of our test. We said we don't want to make a mistake more than this percentage of the time, and our sample's telling us that we'll make a mistake less than that percentage, and we're willing to reject the null hypothesis when that happens. Now it's time to work on a couple of problems. So if you would, open your books to page 427, and we're going to look at problem 16.2. Now this problem says, student counseling. A university offers its students up to 8 sessions per semester of free psychological counseling. To evaluate satisfaction with this service, The counseling office mails questionnaires to 200 of the 1,400 students who participated in the counseling last semester. Only 93 students returned the questionnaire. What is the population in this study, and what is the sample? If you go onto Blackboard, I'm going to put a discussion piece up there, and you guys tell me what the answers you think. Go for what is the population in the study and what is the sample. So now we're going to go and do questions 16.13, 16.14, 16.15, and 16.16, found beginning on page 429. So if you read this problem, it says the distribution of blood cholesterol level in the population of young men aged 20 to 34 years is close to normal with a standard deviation of 41 milligrams per deciliter. You measure the blood cholesterol of 14 cross-country runners. The mean of these 14 cross-country runners is 172 milligrams per deciliter. Assuming that sigma is the same as in the general population, give a 90% confidence interval for the mean level mu among cross-country runners. So let's see how we would work this problem. So here we have that our variable is the blood cholesterol level for cross-country runners. They said that that it had the same standard deviation as men between 20 and 34 years old. So its distribution looks like it's normal with a mean of mu and a standard deviation of 41. Now we're going to take a sample size 14. We get a sample mean of 172 milligrams per deciliter. That means we're looking at a sampling distribution of the mean where it's normally distributed with a mean, that's what we're going to try to estimate, and the standard error of 41 divided by n, which in this case is 14. So there we have our distribution, and they want us to make a 90% confidence interval. So the first thing we look at for 90% confidence interval, the critical value for that is 1.645. So now, how do we make our confidence interval? Well, remember that the general formula for a confidence interval is the statistic plus or minus the margin of error. And what's in the margin of error? Well, we have the critical value times the standard error. And so in our case, for this 90% confidence interval, we have 172, because that was our sample mean, plus or minus the critical value, which is 1.645, times that standard error, 41 divided by the square root of 14. When we work it out, we get 172 plus or minus 18.03 milligrams per deciliter. Now, on a test or a quiz, you could either have the answer like this, where it's given to you as the sample mean plus or minus that margin of error, and the margin of error here is 18.03, or you could be given it into interval form, the 154.0, comma 190.0. And down below is me constructing a 95% confidence interval. And what I want you to note here is, look at the margin of error for my 95% confidence interval. It's 28.2. And so, and there's one mistake, it should be 95. So for the 95% confidence interval, our margin of error is increased to 28.2. So what we can see here is, again, and we've talked about this many times, that as our confidence level increases, our confidence interval width also increases, because you see this margin of error increasing. So this is a great example of the increasing of the confidence level that increases our confidence interval length. And also by looking at the formula, we could see if our sample size would increase. That's another way to decrease our margin of error. So in the next couple of problems, we'll do a hypothesis test, and then we're going to talk about how you find the sample size if you want a smaller margin of error. So in the next installment, that's what we'll be working on. Problems 1614, 1615, and 1616.